from Eyal Cohen, who is the CEO and co-founder of CogniFiber. He has over 20 years experience in industrial and academic background in the field of photonic computing. Okay, so this is a really interesting area for me as well because I happen to have dabbled a bit in photonics, but as well as electronics. But Dr. Eyal Cohen's background is in hardware design, neuroscience, and algorithm as well. So CogniFiber is unique amongst deep tech startup companies by developing an innovative photonic computing system that can accelerate AI more than 100-fold. And as I hinted at earlier, not simply as an interconnect technology like other photonic plays. So the core of this is that light and the photonics have the opportunity to make artificial intelligence even more accessible to business, hospitals, and law enforcement, leading to growth and improved life quality. And this is largely because of the efficiency that can be gained through much higher speeds. And there's nothing faster than the speed of light, of course. So I'm very interested to hear what's going on at the very border, where electrons turn into photons, and with Eyal's talk on pure photonics, reaching 100 million tasks per second within 300 watts. Thank you.
Thank you, David. It's done? Yeah, now it's on. Thank you for the organizing, for having us. ValleyML is a truly very exciting opportunity for us. I think we are the youngest, probably the youngest startup here. It's only 4 years since it was founded.
Sorry, give me a moment here.
Yeah, and it's actually our first exhibition and first time in California, first time in Silicon Valley. It's really, really exciting to be here and actually meet
Click to make sure it's
all the. Okay, so about 8 years ago, here. Finishing my neuroscience PhD, and this is after being a hardware engineer and also machine learning engineer at several startups. Some of them are quite famous, like Mellanox and Saifan, who did flash memory. And I understood that deep learning will need a new type of hardware in order to scale in the future. And photonics was really at its start. And I approached then Professor Zalewski, now my co-founder, and started this journey and thinking of how can we make AI really faster with low power and low heat dissipation. So our mission in CogniFiber is very, very ambitious, but we are tenacious in getting there. Eventually, we want to see system mainly in data center, but also on-prem, not as in, of course, on the edge itself, but micro centers servicing the edge, which are at least 1,000 times faster and 100,000 times more efficient in energy. So I guess all of you are quite aware what is happening today in data centers. Limitation of bandwidth, of power, of heat generation, and of course in expense for many businesses. Using AI is just too expensive, and we need to tackle it. But now also, if we look at the later coming models, like transformers with over 100 billion parameters, it might take weeks to months to train them. It may cost millions of dollars to train them, and a huge carbon footprint of every training. That's facts that are taking now, and these transformers are getting more and more popular. So on one hand, we have the current performance of hardware is going down with a number of parameters. That's really easy because the resources are limited. So it can do billion of tasks per second if it's really small machine learning. But when you go to image processing, it will do hundreds of thousands or tens of thousands of images per second. But when you go to transformers and heavier models, it will do just several tens or several hundreds in a second. And it goes down. If the models are growing larger, it will slow down and slow down. On the other hand, if we look at the carbon footprint, it goes up with the model, as I said. And if we take both trends together, we are at impasse. Impasse regarding sustainability of AI hardware. And you know that today, if you want to be compatible in a few years, every company will be limited by its carbon footprint, computational expense, then this won't do. I mean, already now we are approached by large companies, tier one companies, saying, we want to talk to you because you might be one of the only options that we have to reduce carbon footprint. So if we look, the main technology today is silicon chips. This will still be the dominating technology probably in the coming years, but if we want to be sustainable and scalable, we need to think otherwise. We have silicon photonics, which is a very nice new technology coming out of MIT labs initially in 2015, but still is a very young technology. It has its own limitation, especially if you use phase or coherent computation. You have phase noise, and scaling these chips and their yield is a thing that need to be taken in account. On the other hand, we have a very robust and sustainable technologies coming from optical communication. And it's not a secret that if you look at the supercomputing or pods, or super pods built by NVIDIA and others, they use optical communication as a basic information transfer between servers, because it's really fast, it's low power, it's efficient. So why not take it into the compute itself? That's the idea. Of course, when you do the computing using fiber optics and optical communication, you have the advantage of the interface, the fiber. You can inject huge amount of data very quickly. We use at least non-coherent computation, so we avoid phase noise. We use amplitude of light. But on the other hand, we have the issue of size, of course. It's much larger than a chip. It's much larger. But we need to consider it, but still, because it might be the only, let's say, sustainable and scalable option in the future. And of course, data centers do not lack in space. So the question is, how many pods will I replace with a single large system that I can build? Okay, will it be replacing 4 pods, 10 pods, or 100 or 1,000 pods? And there I can get the space. Okay, so the general idea when we started was about turning fibers into a processor. And it's a very, very different way to think, because all of us know fiber optics. We know that fiber transmit information from point A to point B, very high efficiency. That's why we have the internet, because back in 75, the underwater cable was replaced by fiber optics, and thus the speed of information and internet as follows accelerated greatly. And today we move huge amounts of data through fiber every day. But how about instead of just using the fiber as moving data from one point to another, let's use it as a processor. Let's process the data on the way instead of just at the target. So we thought, how can we do it? And we took a multi-core fiber. That's a fiber with several cores being used today already in communication. And let's play with the cores, their location, their spacing, and there we can get interactions. And these interactions, if we control them, we can get compute. So instead of having an image transferred from point A to B, we can inject the image and get an answer, an AI relevant answer on point B, where we get it. Of course, these won't be very long fibers, much shorter, much more stable. Let's say a few centimeters, tens of centimeters, that's it. But the speeds, of course, will be great. So how can we do it? So that was the basic research. Again, so first we took these cores and we grouped them in small groups. Within the group, the spacing between cores was very small, something around half a micrometer up to 1 micrometer. Between the groups, there were a larger space. The spacing today is normally 20, 30 microns apart in regular fibers, and that's one. So the structure, and I'll show you an example later, the structure of where the core are set, like in ASIC, what is the, let's say, ability of this device to compute, how the data flow will flow in the device. And we have also a dynamic way to control the flow and the mathematical application using amplification within the fiber. So I don't know if any of you come from optical communication. It's very easy to amplify light within fiber. You use a second wavelength as a pump light, then you can amplify the light. And amplification, like any other, there is a linear regime and a nonlinear regime. And depending on the amount of amplification, we can have linear function or nonlinear function. Okay, so we can use amplification to actually program like an FPGA, but instead of an FPGA, we can program the light passing through the fiber and the mathematical function it will operate or implement. I'll give you an example. We wanted, during our research, to show how can we introduce this network, 4-layer networks, a bit of convolutional structure, into a single fiber, a single multi-core fiber. So this is the structure. It's 72 cores. It's not something that is impossible today, with 24 inputs and 6 outputs. The inputs are here in pink, and in gray, these are the 6 outputs. Okay, so this is how you can plan a network, and this could be, of course, one building block of a larger network. And because the inputs are fibers, the outputs are fibers, you can easily connect them, easily scale them. But it's a physical network. Okay, you can treat it like a GPU core. If you have many of these and everything is connected, and then you can play with how to use it, how to program it. So how the light passes through such a device. We have an input coming at the circumference here in cyan. And when the light passes through the fiber, it actually doesn't go only at the Z direction. At the fiber direction, it also spreads in the XY axis, like that. So it goes from the first layer here to the second layer, to the third layer, all the way to the output. So this is a brand new device or thinking. And this is how we can compute on top of this network, which is a hardware network, by just injecting the light into the fiber. I guess you all can imagine what the advantages of this type of computing can be, because you can inject each one of the channels in speeds up to 800 gigabit per second in a few years. You can imagine if you scale this up, what would be the input-output interface? What would be the tremendous speed of compute, latency, and throughput? So this was very clear for us that this is a really great potential for future computation, but it's not trivial how to build this kind of hardware, how much time it will take. Of course, there's a lot of physical. It's as if we went back to 1954. We are in the vacuum tubes, and now we want to go from the vacuum tubes into the transistor age. If we parallel this, we are now having this great idea, but we need to understand how to build it correctly, how to define it, how to manufacture it. But the idea is that if we take many of these fiber, in this case, each one of them is a hexagon. It's a processor, like a GPU processor. Each one of these can have up to hundreds of thousands of cores. Each one of them can be programmed to do a specific network activity, like a convolution filter. And we can program them. And then because they are photonic, they can sit side by side. They don't heat up. They can talk to each other via direct connection. They don't need buses. Just as the light passes through, you can imagine that, let's say the inputs are on this corner, starting from several tens of processors, and the information can flow across this array of processor to any direction as we program it, and it eventually goes out to the output processor. So 1800 processor, that's amazing, can sit side by side, each one of them receiving tens of terabits per second in speed from standard fibers, and do a computation which is now just imaginary. And the amount of processing is something that has to do only with supercomputing. Today, it's about 2.4 petaflops per each processor. You can multiply this by 1800, you can get a huge amount of processing power. Its efficiency is over 1,000 TOPS per watt, and this is more than 10,000 fold than today's. And of course, on top of this hardware, we'll build the relevant software. As Shri told us, it's very important to have, of course, the user side, but this will be the endpoint. So after 4 years and 2 POCs, we are slowly getting there, building one block after the other. As I said, the vision is very ambitious, but we are a very tenacious group of engineers. So at first, we built a small, simple machine based on an FPGA who just gave the data, injected via transceivers into our systems with one first photonic device, 7 inputs, 7 outputs, which was used like the first neuron. We had VOS attenuators here for weighting, and the output went through amplification, optical amplification, as I told you, for nonlinear function. So this was the first POC we built in our seed, and what we showed, we can get an activation function that is the basic function of a neuron. Here, the x-axis is the weighted input. The output axis is the probability of the output to be 1. And what we showed that if we use this first POC, we could get 160 acceleration and 80x in efficiency, even given the noise we had. And this was the first proof that our approach is viable. Then we decided we go into Arrowhead in the company. One will be to bring simple products into the markets to show that our approach is good and the team is capable, we can design products and bring them into the market. And we focus on anomaly detection for industrial IoT, cybersecurity, and fintech. That will be available, let's say, in a year, our beta. That's I'll talk about the roadmap in a second. But on the other hand, we still look ahead to the vision and continue to build prototypes of the multi-core fiber with Erbium. We already had one prototype with Erbium doping with 7 cores, and we are going up to 37 cores. And eventually, we want to reach that device that I talked about, a full network within a single fiber. And this will be the basis for our future supercomputing devices, which I talked about. And this will be fully programmable and will support any type of AI models that you can think of. What we launch here today in ValleyML is our second POC. We call it an MVP because it's already an industry-grade prototype. You can inject data into it. You can read out the data. You can train it. You can do inference. It's still a very modest POC, but still it's a second step, a very important step toward our goals. What we use here, we used, again, an FPGA board to control the flow. Today, it's a 10 gig interface. It will be gradually scaled to 100 gig interface. The FPGA controls analog lasers, which inject the data into the photonic system. And we have layer by layer containing array of weights and electro-optical neurons. Very simple, but very fast. I say simple. It's not simple to make them. It's not simple to design them. It's not simple to have everything connected, of course, in these boxes. But this was a 1-year project, only 1 year. So we raised our A series May 21, and this is already our second step. So we are a small group, but very nimble, as David said. And you can imagine what we can do now with $10 million, $20 million investment. The sky is the limit. We showed that we can do that. We're very limited resources and still get a very good result. This is a 4-layer classifier working at 100 million tasks per second with under 300 watts. Again, we can use it, as I said, in these verticals. It's maybe less important, but the function of an autoencoder, and we aim for an autoencoder, are anomaly detection, but it can also do denoising, dimensionality reduction, and also as using it as a GAN, generative adversarial neural network, we can generate synthetic data using autoencoder. And this will be, again, our next project. So if we look at the numbers, we want to compare apples to apples of our future autoencoder coming in about, let's say, somewhere between a year and 18 months. This will be a 9-layer network working at speeds of 50 gigahertz. We are going to elevate the input speed up to 50 gigahertz. This is in million tasks per second. And the cost, we're going to reduce costs about 15 times compared to NVIDIA DGX, and about 3 times compared to our main photonic competing company, LiveMatter. In terms of efficiency, you can see 20x versus NVIDIA and about 12x compared to LiveMatter. Of course, it starts a bit smaller in terms of volume to compute compared to NVIDIA, a bit larger than LiveMatter, but we are scaling down as we are now having already made our first glass-based chips, which will help us to scale down, especially the matrix, weighting matrices that will dominate the volume in the future. Okay, so these are the expected numbers of our products. In general, we are going to have it released during the coming year. We look for serious companies to have a POC together with us. So if you know anybody interested to go into photonics, this type of photonics will very help. You can also come in our booth and to have more information if you want. And I think that's it. I guess, I don't know if there's a lot of time. So there's more time. Yeah, we can do some Q&A. I was a bit faster, but if you have any questions, I'm sure this field is quite new. I'll be very happy to answer.
Okay, please come up to the microphone and ask away. While you're moving, I've got a couple of questions. So, Eyal, sort of one of the things I've always thought about that was interesting in Silicon Valley is, as more predicted this exponential growth,
yeah.
Right? And you know, as the geometries decrease, right, the path forward was very clear, right? And it was also investable because it was a 2x per 18 months.
Yeah.
But as I know from my background in photonics that you know, light is light, its wavelength is fixed. You don't get smaller than 450 for blue and that's it. So how do you see the path forward for photonic-based solution?
Yeah. First, I'm going to say that I won't be the first one that's saying that Moore's law is probably not as it was. I mean, definitely not in the number of transistors per die. But in general, there is a problem also getting the transistors small because of interference and data stability issues. But in photonics, everything is of course larger. I mean, any photonic element, because of the wavelength of photons, is at least 10 by 10 micrometers, which is far larger than a transistor. But on the other hand, the bandwidth of photons is far, far larger. So for each element, you can inject as many as 100 wavelengths, different wavelengths using multiplexing. And each wavelength you can modulate up to 50 gigahertz. So I don't know if you know, but the record for a single fiber, the amount of data you can transmit, the record was done in NTT labs, was set at 1 petabit per second. That's per a single fiber. Now imagine the machine I told you about, which has 100 fibers as input. So potentially it could house 100 times 1 petabit per second. That's 100 petabit per second interface. That's something which is inconceivable. Yeah. So of course, we don't aim for a very small size computing machines. Quite, well, let's say we will start from 2 pods, 8 pods, 10 pods, but these 10 pods will be able to calculate the whole computing done across the whole world today in a second. So, of course, data center is not small. We'll just use a portion of a data center, but we'll be able to accelerate. And as I said to begin with, sustainability will be the main issue that will contribute to. And to reduce the power consumption and heat generation of data center by 90 to 99%. That's the main target. Yeah.
Thanks for a very nice talk. I have a few questions, but given the time, I'll ask my first one. So when you showed the architecture, it seemed like it was mostly feed forward, but you also mentioned about training. So I was wondering, in a like in and gradient kind of methods, right? How do you do backpropagation using this architecture?
Excellent question. Backprop, of course, there are two ways to do photonic backprop in general. So either you sample every way along the way, right? And that's a major question. Today we do sample every layer and every neuron. We can measure exactly what and do the backprop. Another method to do backprop using photonics is to inject the light in the reverse direction. And this is how it was done in several demonstrations in research. But when I talk about, let's go back to our vision. Yeah, here. So for each one of these processors, there's 6 ports. Each one of these is a port, input-output port. And as they sit next to each other in this beehive formation, each one of the processors is connected to the 6th processor around it, okay? And it's a back and forth connection. So how do they connect? They connect through a U structure, like a mirror. So the light goes out from one and then go back into the other via these ports. So what we do is we can sample using photodiodes array and sample what's the communication back and forth, and we know what we need to get during the backprop. Of course, it won't be a straightforward backprop. We need probably to modify it a bit to our needs, but this is how we sample at least the input and output of every processor within, and this would be our window of sampling. Of course, we can also reconstruct using emulated model, we can reconstruct what's happening within the network itself, but this is a different question. Yeah, but we do understand this challenge and we are ready to face it. We have several directions.
Yeah, another question is, are you worried about form factor? Because if you were to scale this, right, how many of these hexes and these U connections would you need, and would you get limited by the form factor of racks and stuff like that?
So this machine is, we expect it, as I said, to be a pod size. In terms of production, probably would cost several millions to build, but it would generate that capability to process about at least 200 giga frame per second. For example, if we talk about image processing, 200 giga frame per second is about 1 million times faster than one we have today. So take a machine let's say per image, and reduce its price, you'll get to at least a 1,000 times reduction in cost per image. And of course in power, because this whole pod will take about 20 kilowatt, which is, if you divide by the number of image processing, you'll get almost 1 million factor in terms of efficiency. Yeah, so it's very hard to make it. Of course, it's a challenge, but when we get there, it will definitely be a solution for sustainability and bandwidth.
Excited to see that.
Thank you
so much.
Any other question?
Last question.
Yes. So for edge problems or edge solutions, what are the challenges of miniaturization? And then in terms of computing, how complex it can get playing with the different amplitudes?
Yeah. Okay. So first for edge, definitely, as I said, first, if we look at edge, we're not talk about replacing a chip on a camera or so. We are talking about, let's say, front end, micro centers, let's say for controlling a neighborhood or a large complex of, for example, industrial factories, which all will use this one pod as their real-time processor because of the low latency and low power. But for smaller application like a server size, we are thinking about downsizing, and then we'll need to combine, of course, chips. And at the moment, we are looking into glass-based chips. We already manufactured 2 types of glass-based chips in France. One of them has to do with conversion of photonically conversion of digital to analog and vice versa. And the second one will be about the matrix of how to implement a matrix of weights, but very reduced on a chip. So we do consider, of course, downsizing. Again, as I said, I don't think it will get to electronics chip size ever. I think server size will be the minimal, let's say 2U, 3U, maybe 4U will be the minimal size of any photonics system that has any commercial meaning. Regarding the other questions, of course, all the computing is done here is analog to analog. Only the input and output are digital, but in this case, in the vision, we inject directly the fiber as they come in communication. That's the 50-50 communication cables will come directly into the system. So we don't even need to change anything. So we take the data as is, as you send it to us by 100 gig, 200 gig, and then we use it as the light itself that's being sent. We amplify it a bit in every junction, of course, but this will be used as the data injection. We don't need to re-inject and regarding the accuracy or the bit depth, we are now starting with 4 or 5 bits analog computing, and we'll get to at least 8 bits. Of course, I don't think we'll get beyond 8 bits, but 8-bit models are quite doing well in AI today. So I think we'll manage, and we do have other strategies how to make it more accurate. For example, in some cases, doing averaging over several computations in order to reduce noise.
So
yeah.
To me, after looking at all your performance characteristics, it sounds like you may have a problem finding the right problem space to where your solution is good.
So,
because if you throw in 200 giga problems per second, then yeah, you have a solution for that.
yeah.
But I don't.
Do we need it? You ask, do we need this?
Do you see any such problem space where you will have to answer a question 200 billion times per second?
You can ask NVIDIA and you can ask Meta or Facebook. They all want to have an omniverse, dataverse, metaverse. And if you want to have these verses, you will need huge amount of computing for any user every second. Images processing,
it's
rendering.
It's not the amount of computation that's the problem. It's the amount of problems per second to solve.
No, I think there will be huge demand. If you try to say how many users will use metaverse or omniverse.
If you use this in a face recognition
Yes.
scenario.
Yeah, for example. Yeah.
You would have to have a requirement that you need to recognize 200 billion faces
But
per
not
second.
for single users.
Yeah, but
You have to collect them. Yes.
yeah, but even then, I mean, there are only 10 billion users in the world.
Yeah.
I think there's probably more than that on Google at the moment,
Yeah.
or at any moment in time.
Yeah.
Well, 10 billion is the population of the world, so.
Yeah, but machine learning will not be limited by the number of users. A single user can have many applications running, although we're not limited. But yes, this is a vision. It's very strong. I think the main issue is to think about the planet and how are we going to use the energy, because now we use 2% of the energy for data centers, and the projections are 10% in a few decades, and this is really ominous for our planet. I mean, especially with the global warming. But now, I think we should at least strive to have a sustainable solution. And even let's say, if the prototypes will work, let's say not 200 gig. If they work 1 gig or 10 gig, I will be happy, because this is already will be a very strong breakthrough. So, of course, this one is not a year or two. It's a long way, but as I told you, we have a very tenacious team, and we're gonna get there.
So, Eyal,
Yeah.
let's pause here for a moment. We want to
Yeah.
welcome down the panel.
Yeah.
Shri, if you're in the audience. Okay. So selfishly, I've got one question to ask you.
Yeah.
So I'm also interested in quantum aspects and quantum computing.
Yeah.
And of course, in light, there is always the opportunity to use and leverage quantum. So is there a roadmap forward that you're not talking about into the quantum realm?
Yeah. Quantum is really interesting. I think it will be the next revolution in maybe 10, 20 years from now. But still, like in the first silicon photonics, they now have to solve the first issues of noise and how to control many qubits. In general, whatever hardware we build probably will be suitable also for quantum, or at least with mild modification in the input and output. We look at Xanadu, for example. We monitor, we're following them.
Hang on a second, I just want to pause for a moment. I'm not sure everyone in the audience got that.
Oh.
What Eyal just said is that his infrastructure is amenable to quantum computing
As well.
as is.
No, I said with mild modification. I won't say as is, with mild modification. But in general, we do have IP also in quantum, and we are studying it. And when quantum will be ready, we'll be ready for it.
Yeah,
Yeah.
thank you.
Thank
As
you.
I know well from the photonics space, there's a lot of opportunity once you've got the
Yeah.
infrastructure.
Yeah.
Okay, thank you.